Hello everyone, today we will talk about image inpainting. What is inpainting? The definition in Wikipedia is inpainting is the process of reconstructing lost or deteriorated parts of the image and videos. The main applications of image inpainting are photo restoration and object removal. Here we see a painting that has a lot of degradation. And here is the restoration of that painting. This work is done by experts. Of course, we can use the computer to do the same thing. We will see this later on. Another example is about object removal. In this case, we see nothing wrong with this image. However, this was the original image. Now we will talking about how can we use computer to do image inpainting. In general, image inpainting can be classified into two categories: traditional image processing based and deep learning based. We will introduce the exemplar-based method first. Region filling is an old but classic exemplar-based method. Here we see 4 images. We call the region to be filled the target region, and this counter is denoted by theta omega. This part is called the source region. Phi, it provides sample used in filling process. For each pixel in the image, we call the square centered on this pixel the square template, indicated by psi sub p. Suppose that now we want to fill in the missing part in this square template, so we want to find the best match patch from the source region. These two patches is the most similar to these parts. We see that if psi sub p lies on the continuation of an image edge, the most likely best matches will lie along the same edge. The algorithm of region filling is shown below. First, given an input image, the user select the target region, the source region, and specify the size of template window. Next, we will iterate the following 3 steps until all pixels in omega have been filled. Step A is for each pixel on theta omega, compute patch priority and choose a pixel with the highest patch priority. You may wonder why we need to compute the patch priority. That is because the filling order is critical. Here we see this is the input image, and these 2 pictures are inpainted using different order. As we can see, the second order has better performance than the first order. After choosing the pixel with highest patch priority, we propagate the texture and structure information. That is, we will find a patch in source region which have smallest distance between the selected patch, and copy this patch to the selected patch. The distance between 2 patches is simply defined as the sum of oscillating distance of already filled pixels in the 2 patches. This distance is computed pixel by pixel. Finally, we will update the counter and the confidence value. Let's see an example of region filling algorithm. This is the original input image, and this is the mask. We can see that the region with highest gradient are inpainted first, such as this part and this part, and the region with smaller gradient are inpainted later, such as the river. The region filling algorithm have 2 main disadvantages. First, the convergence rate of this algorithm is low, and next, it's easy to get stuck in the local optimum. To solve these 2 problems, Connolly proposed a method called patch match, which increases the efficiency of searching. Remember that in filling region algorithm, we need to search all patches in source region to find the best match patch. However, in patch match algorithm, we only need to search a small number of patches. Here we see 2 pictures. The basic idea is that if A and C are similar, then B and D will also be similar. Here is the image. A is the target region, and B is the source region. Firstly, we randomly match the patch in B to the patch in C. It means that these patches are randomly selected. Then we iterate the following 2 steps until convergence. The propagation means that for each patch in A, for example, this blue patch, we calculate the distance between the blue patch and these 3 patches in B. and choose a patch with smaller distance, then update the match. This is exactly the idea I mentioned before. The red patch is the nearest neighbor of the blue patch. So if the red patch is similar to this patch, the blue patch should also similar to this patch. After that, we do random searching B. Instead of searching the whole region B, we only need to search the match of its neighbor. That's why this method accelerates the convergence. Next, we will talk about database-based method. The algorithm is not complicated. Here we see an input image, and this is the target region we need to inpaint in. The only thing we need to do is to compare this image with all images in our database and find the most similar one. Finally, we will talk about deep learning-based method. Context encoder is the first algorithm that uses deep learning to do image inpainting. Here are two pictures. This one is the input and this one is the output of the network. We see that it gives reasonable results for large hole filling. The overall architecture is simple encoder-decoder pipeline. The encoder takes an input image with missing region and produces a latent feature here. And the decoder takes these features and produce the missing image content. To measure the result of this net, we need to measure the difference between the ground truth and our output. We also call this difference the loss and the error of the network. So how can we define the loss or the difference between the ground truth and the output? The author defined these two kinds of loss in the paper. First is reconstruction loss. It calculates the difference between these two parts. However, since the loss uses L2 distance, so only use this loss to train the model will output a picture like this. You can see that it's very blurry, so the author add the adversarial loss. Since that loss is come from generative adversarial network, I will introduce this network briefly. The GAN is composed of two networks, the discriminator and the generator. The generator takes a random noise as its input, and it outputs an image. The output image have the same size as the training dataset, and the discriminator takes these images as input. It wants to identify which of these images are real and which of these images are fake. The goal of the generator is to fool the discriminator. These images are all generated by GAN, so we see it's a very powerful network. So in this context encoder algorithm, the author adds this loss, the same as GAN, to improve the image inpainting result. After using the joint loss to train the whole network, we can see that the output is better than before. However, this algorithm cannot generate high-resolution image.
Now we introduce another model, which could deal with high-resolution image. Well, here is a brief introduction of the globally and locally consistent image completion. Compared to the context encoder, it has two discriminators, local one and global one. They serve different purposes. As a result, this model can fill in image of any resolution or any shape. On the right-hand side is the image before and after. So let's have a look at its general structure. This is overview of the whole structure. We can notice there is a single completion network for filling the image and two discriminators for discerning whether it's real or fake. Let's focus on its completion network first. On the right-hand side is structure table. We can notice that it's only decrease resolution for twice, and on the second layers and fourth layers. This is important for generate non-blur texture in the missing region. More importantly, here we use dilate convolution to extend reception field here. What is dilate convolution? Now we have a brief introduction. As you can see in the picture A, this is reception field of a standard convolution kernel. However, in B and C, we get a larger reception field using same kernel. This is what dilate convolution can do. By using dilate convolution, the model can effectively see a larger area of input image. Why is it so important to see a larger area? Let's take a look at picture D. In the picture, here is an empty hole we need to fill in. The omic 1 stands for the reception field of P1, and same for the P2. On the left, when filling the hole, we could compute P1 using the influencing region here. However, P2 could not be computed because omega 2 contains no information outside the hole. On the right-hand side, the problem is fixed by using delay convolution. That is how completion part works. Let's have a look at discriminator part. As you can see, for two discriminator, we have two different input. In the previous step, we have already generated a rough image for the empty hole. We can call it filling part. Then we put the filling part into local discriminator and the whole picture for the global discriminator. After going through two discriminators simultaneously, we can concatenate their output as a long single-dimension vector. And finally, using a sigmoid transfer function to transfer this into one single value. And this specific value stands for the probability whether the image is natural or generated. Based on this well-constructed model, some newly optimized model has been proposed. Let's have a glimpse of model joined with contextual attention. In this model, they adapt completion network in the previous model. Actually, they use two completion networks. This one. The first one is called coarse network, which means it generates image with somehow lower quality. You may see in the generate part that is blurred. The second one is called refined network. The task of it is to refine image that is generated from before. As you can see in the picture, after passing through the refined network, the generate part becomes more clear and more consistent with background, have more details. And at the end, we use the same two discriminator in the previous model. You may wonder, why that simple combination of two networks make such significant progress? The answer is not that simple. Moreover, here is an important layer hidden after the coarse result, called contextual attention layer. Let me further introduce the function of this layer. Firstly, what is contextual attention? The intuition is straightforward, just like human studying. When it comes to a bunch of things, we need to figure out which part we need to focus on. In this case, the contextual attention is just to figure out, in the input image, where should the network focus on. After finding where we should focus on, it would be more efficient to fetch useful information and then use the information to generate missing part. Here is the question, why using attention? Because when we are using convolution to process image, because of the spatial invariant of the convolution itself, we can only fetch information from the neighborhood region. So to overcome this limitation, we introduce these attention layers to the network. Above all, we have introduced several models of doing image inpainting. However, we cannot give a conclusion that which one is better, because that depends on your image and your dataset, and many other factors. They all contribute to your output. So if this interests you, you can pick one or more to try and create your own image artwork. At the end, we have a short demo for you. So let's see some fantastic image inpainting now.
Cause you're a sky full of stars. Cause you light up the path.